Hi, my name is Tommy, and this is the final project for the Duke AI product management. The task for this project was to build a model to predict electrical energy output of a combined cycle power plant provided the following variables. There are four features here and nearly 9,600 data points. The first feature was temperature in certain ranges, degrees Celsius. The second feature was ambient pressure in millibar. Third, relative humidity in percentage. Fourth is exhaust volume in centimeters of mercury. And we had to predict a target net hourly electrical energy output was our goal. The approach I took was linear regression and eventually led to multiple regression modeling. I thought parametric algorithms were the best because there is an assumed form of relationship between the input and the outputs. My approach was to split the data into sections. The first third was a test set, and the remaining 2/3 were my validation sets. Like I said, I did individual linear regression of each individual feature to see if they correlated well to the output. And that led to multiple linear regression of combined multiple features. Finally, I observed the regression statistics for an R-square value to validate the models. And then I used the R-square values of both model 1 and model 2 against the test set equation to see which model was the superior model. For the first model, I used only 2 features. And for the second model, I incorporated all 4 feature variables. Here's my test set data. You can see there are the first 4 columns, and those are my feature variables. And the 5th column, PE, that is the predicted, or that's actually the outcome that was observed. And then on predicted on the very right, that's what my equation output was. Test set with all features for my initial go around. You can see that the regression statistics are good for this test set. This is a 1/3 split with a 0.96 multiple R value and an R-square of 0.929. What I did initially was I took each feature and I did an individual linear regression of each. I saw that the exhaust volume, and the ambient temperature were all correlated well. However, the ambient pressure and the relative humidity seem to have a greater coefficient of error. As you can see, the individual data points are way more spread out versus the trend line. So that led me to think that maybe they weren't as valuable. So for my first model, I decided to discard the ambient pressure and relative humidity features and opted only for a 2-feature model, which was exhaust volume and ambient temperature. So I took the 2/3 remaining data and I ran a regression linear modeling of just 2 features, temperature and exhaust volume. And I found that the multiple R value of 0.95 and the R-square value of 0.91 were the outputs, which are pretty good. I saw that all the p-values were greater than were less than 0.15. So it meant that they were all they were correlated. And I ran a summary output, which was Y is your predicted output, which is the intercept plus all the observed values multiplied by the coefficients. And I got 442 megawatts as my predicted value for this first model. For the second model, I opted to use all 4 feature variables. That's everything available. Also using a 2/3 remaining split of the data, and I found a better multiple R value and a better R-square value using all features. The p-values were all less than 0.15, so they're all relevant. And you can see the coefficients I used in my summary output for my my y equals mx plus b equation, basically, which is a summary output right here. So in conclusion, I found that Model 2 was the best model to use. It was a superior model to Model 1. In fact, using all 4 feature variables is beneficial because you get a greater R-square value than the first model. And I found that the predicted output value you get from Model 2 closely matches the test output as well. So I went with Model 2 using all 4 features as my my go-to model. So thank you very much for watching, and I hope you learned something. Thank you.